Hi boys and girls. Now in this video I will tell you about creating a Verilog module. We will start with a very simple Verilog module, a 2-input AND gate, and the way we write the test bench to test this design. So let me start with that presentation. So the short speech is organized into your learning outcomes, a simple Verilog module. Here I use an AND gate. Then apply stimulus with a test bench, how to test my Verilog design with a set of signals. Then the summary of what you learned. So what you will learn in this video is that you will create a Verilog module for a 2-input AND gate, which is a very simple circuit. Then you will understand the port declaration and the syntax of writing Verilog code. And then you will learn to write a test bench for the AND module to apply the stimulus, how to apply the signals to the given AND gate. Then you will observe the input and output waveforms with the GTK wave. So let us consider a very simple Verilog module. Verilog models everything as a module. So let us look at that AND gate. That is a 2-input AND gate with the input A and B, which are connected to 2 wires, okay, and an output Y that's also connected to a wire. Okay. So I start a module like this. Look at these 4 lines of code. I start with the keyword module and end with the keyword end module. So a module is started and ended with the word end module. Module is started with a module and ended with the end module. Then module, then some name of the gate. Some name can be given. Here I give some meaningful name like AND underscore gate. Okay. Then the arguments are put in brackets, which is followed by a semicolon, just like in C programming. As ended with the statements are ended with semicolon. Now here I declare the input and output ports, like I say output is Y. Output means, and what is the data type? Here it is, the data type is a Y. So output wire Y, comma, so that is followed by input. 2 inputs are there, so I write it as in common, like input wire A comma B. So I have declared the ports also in the first line of the code. So I started a module, ended with end module. Here the module name is given AND gate, AND underscore gate. Then brackets are put, everything is ended with a semicolon. Then within this brackets I write my input and output ports. First I write my output port. Output is a Y. What is the data type? It is a wire, output wire Y, that is followed by a comma. Then input is a data type is a wire, A comma B are the values. Now the concurrent statement within this function, within this module is AND Y comma A comma B, meaning that A and B is ANDed, that output is Y equal to A and B, and Y comma A comma B. That creates my module. The name of the module is AND underscore gate. This I already told you. Line 4 is a concurrent statement. This can be verified. This code can be compiled by iVerilog. So you can observe the if there are no compilation errors, the output file will be written, and I will show you how this compiling is done. Here I go. My code resides here. It is andgate.v is a file there. Now I will make it bigger. Okay, it's sufficiently visible now. Now my code is here. This is my andgate.v. You can see with a nano or any editor, and underscore gate.v. You can see that this is my module. Here you can see that these two slashes, they are used for commenting. So here some comments are given, like module name is AND gate. It's a function is 2 input single AND gate. Okay, here the same code is written. So this is how it looks like. Now I escape this. Now I run this with iverilog and get and underscore get dot v. I can specify some output file also, like -o and underscore, or I will say simply write and get dot o. Okay, now the file and get dot o is written now, which is an executable. I have an executable here in this color. This is an and get dot o. I can run this and get dot o, but nothing happens because I haven't given any signals to this or any tester signals to this, so nothing happens. So this is how I check the functional correctness of the Verilog code. Now let me go back to my presentation. Now this is not enough because one way you can test is you can write it into an FPGA board, like a tiny FPGA. I can test with real signals that you may be able to do in the lab. But here what I do is I test it with a test bench. I write a separate program for that. I write a separate Verlog module for this and test with the test signals. Then I dump these testing signals into a file called a VCD file, or value change dump format. Then I view it with a waveform viewer. I view this VCD file with a waveform viewer like GTK wave. So that I will explain to you. So applying stimulus with a test bench. So a Verilog test bench can be written to apply stimuli to the above module. So that test bench is shown below. What this test bench does is it applies signals to this Verilog module I have written and dumps these signals in a .vcd format. So the .vcd file can be then viewed with a GTK wave. So you can see the operation of the AND getting performed there. Now you can see this thing. Maybe it will be better if you see it in an editor. I will show it in an editor. This is a test bench for that. First, some description is there that is commented by these two slashes. That is test bench for a single 2-input AND gate. This is a description given so that others can understand that. Then the second line, if you look here, you can see that it is some grave include AND get.v. This is my original file AND get.v. I will open that for you. This is my AND get.v. This is the module I just said about and get output wire, input wire AB, and some name is given and YAB. This is my AND gate. So my AND gate is included here. This is started with the grave sign. This is actually the symbol grave accent. Okay, this is a grave accent symbol. So this is grave include AND get.v. So that AND get.v should be in the corresponding directory, or some path should be given. So that grave is just like your hash include some header file in C programming. So here instead of the hash we use a grave symbol, a grave include AND get.v. What it does is my return Verilog module is included now. Now I have to write a test bench. My device is included in this. Now I have to write a test bench. So what is, I start with a module test bench. Some name can be given. You can write an AND test bench or something. Here it is written as what do you call it, simply as a test bench without any parameters. You can see that here there is no parameter, unlike the Verilog module. No arguments are given here. Now you have to carefully understand this. Here you see that register AB, meaning that it is not given as a wire now. It is, the inputs are not given as a wire now, but in the device they were given as wires. A and B were wires and Y was a wire. But here we are applying stimulus to that. We are storing some values and giving to that. So they are indicated as storage elements. I told you registers are for storing storage variables. So here I write reg AB, A comma B, and output is a wire, because output I am not storing anywhere. Output is my wire. And what I do is, now I have to use this AND gate AND gate. Here I take an instance of this AND gate and apply on A, B and Y. So what I do is, my format was and Y comma or A comma B. So likewise here Y is my output. So what I do is, I write AND gate x1, it is some name, x1 is some name, then Y comma A comma B, that creates my AND gate. Okay, so my module is an instance of my module is also taken. So at first I included my file, then I declared my input outputs etc. Then my gate is applied, or my device instance is taken. Now once that is done, you have to test it with the signal. So for that you use some system commands. So these system commands are often preceded by a dollar sign. What I say is, one I use is monitor and the other is dump. So here I initialize with the keyword initial, then begin and end. These are syntax you have to understand: initial, begin and end. Then dollar monitor. Dollar monitor is for monitoring this change of signals, or how the circuit behaves with the signal. So monitor percent time, percent dollar monitor dollar time, dollar sign should be given for this system commands. Monitor this dollar time, comma, time is my simulation time actually. Then Y equal to percent B, A is percent B. They are binary variables, meaning that they are binary variables. Just like your in the C programming, you use some percent F etc. Or percent D that way. Likewise here it is a binary variable. They are bits actually. Y is percent B, A is percent B, B is percent B. B is my value here, my input value, that's binary. Then Y comma A comma B, backslash just like in C, Y comma A comma B. Okay, so this Y value is mapped here, A value is mapped here, B value is mapped here. Okay, then end here. Then you write another initial, another dump, another thing, another initial, begin end. If you say begin end, okay, here I apply my signals. Okay, here I create a dump file and get.vcd. Any name can be given. You can give a.vcd. I just give and get.vcd and underscore get.vcd. You can give any name. This dump wars.c is for dumping to level 0. Yeah, that you will understand as you go along. Just keep it there. Dump wars 0 means 0th level, dump to the 0th level. Okay, now I have given some input and output signals. You can say that A equal to 1 bit. This means that a binary, it's a 1 bit thing. So A is a 1 bit variable, that is value is a 0. B is a 1 bit 0. So initially up to 5 nanosecond, A is 0 and B is 0. Okay. Then at 5 nanosecond, A equal to 0. Okay, this is a 1 bit variable. 1 bit variable. So you can give only, if it is a 2 bit thing, you should say 2 prime B0, B0 0. If it is a 2 bit variable, I should say A equal to 2 prime B0 0 or 1 0, something like that. Here it is a 1 bit, so it is A1 B0 means A1 B0 means it's a 0. A is 0, B is 1. Then A is 1, B is 0. A is 1 and B equal to 0. Here another after another 5 nanoseconds, A is 1, B is 1. So then this is finished. Okay, dollar finish is another system command. Here you begin should be ended with end. You end the module. You started a module here, module test bench, that is ended with this thing. Now if I run this thing with some output, you can see these waveforms. I will go to that. The name of this is and underscore tb.v. I will run it here. tb.v. I will specify some output, some a.out. You can see that it has been compiled without error. You can see this file and a.out here. You can see this file a.out here. I run this file /a.out. Now you can see that some VCD file has been dumped into my directory. What is that file? I can say that it is AND gate AND gate dot vcd. I have written a file AND gate dot vcd. Here you can see that at 0 nanosecond it is y equal to 0, a equal to 0, b equal to 0. At 5 nanosecond a equal to 0, b equal to 0, y equal to 0. It's an AND gate. Only if all are 1, both are 1, it becomes a 1. So here at y equal to a at t equal to 10 nanosecond, a equal to 1, b equal to 0. So again it is 0. At 15 nanosecond I have got a equal to 1 and b equal to 1, and y becomes a 1. Now you can see this as a waveform by invoking GTK wave. I will type here GTK wave and underscore gate dot vcd. You can see that the waveform viewer has come. If we type here, you have this wire A coming here. I append that. Okay, wire B is there. I append that. Okay, and wire Y is there. I append that. Okay, you can see the three signals here. A is 0 from first 5 nanosecond. Okay, then remains this comes here 10 nanosecond. Okay, y is 0 from 0 to 10 nanosecond, and then it is here it is b is 0 up to 5 nanosecond. Again it goes high, then goes down at 10, goes high at 15. Now at 15 you can see that both signals are high, so my AND output here it is low from 0 to 15, and then from 15 onwards it becomes a high. So that is the operation of the AND gate. Okay, so you can write this a couple of times and execute this, and you understand the behavior of the circuit. So now when I come to the summary of your understanding, if you see what you learned in this video, or you learned to create a Verlog module for a 2-input AND gate, then you understood the port declaration and syntax. You can do more examples and you will familiarize that. Then you learn to write a test bench for the above module, and then you observe the input and output signals with a GTK wave. And that is the end of this video. I thank you all.